Hey, welcome back to Math with Patrick. It's March 25th. We have problem number 84 to solve from this Daily Epsilon calendar. And the answer is 25 because that's today's date. So it looks like we need to solve for y, and y is going to be this infinite sum. And once we figure out what y is, we can plug it in here, and 1 divided by y should be equal to 25. And just to kind of figure out what y should be, is if I do 1 over 1/25th, this is asking how many 25ths fit into the number 1, or in other words, just 25. You could also think about doing some fraction division, where if you do 1 divided by 1 over 25, if you change this to multiplication and find the reciprocal or the flip of the last fraction, you get an equivalent expression. And so this is still just 25. So essentially, I just need to show that this infinite sum that's equal to y is 1/25th. So let's show that y is equal to 1 over 25. Let's just figure out what this sum is going to look like. It is an infinite sum, so we can't write the whole thing, but I could plug in these numbers and just kind of figure out what this sum is going to look like, at least the first few terms. So the way that sums work is you just plug in this first value anywhere you see this n, and then, well, you'll write that first term down, so it'll be 1 over, and then 6 to the power of 1 plus 1, or 6 to the power of 2. It is 32, but I'm just going to keep it in exponential, or sorry, 36, but I'm going to keep it in exponential form for now. And after plugging in the 1, then you're going to add the next thing, and that's going to be when n is now equal to 2. So I have 2 on the top, and then a 6 cubed on the bottom, which is 216, but just to be concise, I don't need to write that. Then we're going to get 3 over 6 to the 4th, and then probably now you can kind of see where this pattern is going. Let's just do one more. Plus 4 over 6 to the 5th. And because we don't have a top number, or rather it's infinity, this will go on forever. And maybe you're thinking, wait, if we're going to add an infinite amount of things, won't we just keep going on forever? But sometimes these converge or approach a number, and I'm trying to show that this sum is approaching 1/25th. Just, I guess, kind of looking at the values here, we're starting with 1/36th, which is smaller than 1/25th, and then we're adding on 2 216ths. And so this is already really, really small. All of these numbers are really tiny. And so adding all of these up should get me 1/25th. But it's really hard to show that, and I'm not about to add up an infinite amount of terms. So let's take a little break, and I want to prove something about geometric series. A geometric series is one where you multiply to go from one term to the next, just like how we're this one isn't a geometric series, because we're not just multiplying by 1/6 to get from one term to the next. We also have this changing numerator. So that part's going to be a little bit weird, but I have an idea for how to deal with that later. So just with normal geometric series, you can start with some value, let's just call it a. And again, I said you multiply to get the next one. And so we would do a times some value r. R kind of stands for a ratio or a common ratio, where you can multiply by r to get to the next value. And so this is an example of a geometric series because I start with some number and I keep multiplying by r to get to the next one. And let's just go up to, say, a times r to the power of n. Why not? Let's say this is some sum up to n terms. I guess it'll actually be n plus 1 terms because we have the 0th term right here, the first term right here. And basically, I want to find some kind of closed form equation for this. I would rather not have these like dots right here. So there's a little like algebra trick here where if you multiply both sides of this by that common ratio r, we're going to get AR to the 1 plus AR to the 2 plus all of these terms, AR to the n plus 1. Then if I subtract one from the other, I'm going to do, I think let's do r times the sum minus the sum. Basically, it's this bottom sum, all of these terms all added up, and then I'm subtracting away this top one. If you notice, these AR1s and AR2s cancel out if I subtract them. And also, basically, all of these middle terms are all going to cancel out, except for like a few of them. I think just two of them, actually. Because if I do this bottom sum minus this top sum, all of these terms are going to cancel out, except for a r n plus 1 minus, and it'll just be a, because again, r to the 0 is just nothing, it's 1. And so now I have some kind of shorter version of my sum. I want to isolate s sub n, so I'm going to factor it out here. I get an r minus 1, and I still have a times r to the n plus 1 minus a. And you know what? Why not? Let's factor an a out here as well. Factor this a. And then finally, to get the sum by itself, I have a times r to the n plus 1 minus 1 over r minus 1. And since we're taking an infinite sum over here, let's think about this series being infinite now. And if our common ratio is less than 1, or I guess rather if its absolute value is less than 1, try to imagine what's going to go on here in a second. So if r is, the absolute value of r is less than 1, and let's also say, and we have an infinite series, that basically just means I'm adding up an infinite amount of numbers, kind of like what we were doing for this problem for today. I'll do s sub infinity. That infinity just says that I have an infinity amount of terms in the sum. And basically, I'll just replace any time I see an n with an infinity. And it's just going to be this top one right here. It'll be r to the power of infinity plus 1, but that's basically just infinity. I still have this minus 1, and it's r minus 1 down here. And if the absolute value of r is less than 1, basically what I'm doing is I'm multiplying some number that's less than 1 to itself over and over and over and over again. So if you think of like 1/2 and you do 1/2 times 1/2 times 1/2, you go like a half, a fourth, an eighth, a 16th, 1 over 32. That number is dropping down to 0 really, really quickly. And if you do this multiplication an infinite number of times, it's actually equal to 0. It's not essentially 0, it is 0. So I'll have a times a fraction of 0 minus 1 over r minus 1. And essentially, it's just a negative 1 up here. And basically, I guess I'll show all my steps. It's a times negative 1 over r minus 1. But I do like it a little bit when it looks like this, a over 1 minus r. I scooched the a up here, and then I got rid of the negative sign on the top. And so I kind of also got rid of the negative sign on the bottom. If you negate a difference, you can swap the terms essentially. Like 5 minus 3, if you negate that, is the same thing as 3 minus 5. They're both negative 2. So now I have this really convenient closed form equation for an infinite sum. And this, let's see, what is this infinite sum even going to be? It's a plus ar to the 1 plus ar to the 2. So just because now we're going into calculus, instead of r, I'm going to use x, because for me, x just makes more sense when I'm working in calculus. Basically, what I've just shown is that a plus ax squared plus ax cubed plus etc. plus AXN. And here we can assume n is infinity because we have an infinite sum. This long-term sum here is just a over 1 minus r. Oh, 1 minus x. There we go. And let's bring it back to the problem today. So the issue I had earlier, this isn't a geometric series because we aren't just multiplying to get from one term to the next. We also have this incrementing numerator here. And calculus is going to help us match that kind of pattern. If I take the derivative of both sides of this equation, I'm basically going to do a whole bunch of power rules over here. And then I guess it's also kind of like a power rule over here. Maybe it's kind of like a quotient rule, depending on how you look at it. And I think I'm actually going to scooch that a off to the side for now, because it'll help me get rid of that coefficient when I take its derivative. So this one is just 0. So let's see, we're taking its derivative now. This one is going to be just a. This one will be 2ax. And so what I'm doing here is I'm taking this power and I'm bringing it down, keeping the a there, and then decreasing the power by 1. And this is just kind of this power rule that you might learn if you take a calculus class, or maybe you already know it. The next one will be 4ax cubed. Then we'll have 5ax to the fourth, etc., etc. And then that's going to go on infinitely because we have an infinite sum. And taking the derivative of the left side, you can keep these multipliers alone when you're taking derivatives. And then how about I'll think about this as a little bit of chain rule and a little bit of power rule. This is the same as 1 minus x to the negative 1. So employing that same power rule, I'll bring this exponent out front as a multiplier. Then I'll keep my inside part the same, and then I'll decrease my power by 1. And then the chain rule is an important derivative rule now, where if I have some kind of function expression on the inside of another function expression, I need to make sure that I multiply by the derivative of the inside part, which is negative 1, because the derivative of 1 is 0, the derivative of negative x is negative 1, and then doing the 0 minus 1 gets me the negative 1. So ultimately, if I simplify everything on that side, it's a over quantity 1 minus x squared. Those negative ones cancel out. All right. And then what do we have on the left side? Well, we have this a in every single term. So why not? Let me just factor it out. And then I have 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the fourth, so on and so forth. And let's see how this relates to the problem from today. So I'm noticing that this 1, 2, 3, 4, 5, those just coefficients you see at the front, I'm trying to line them up to the numerators here. And then I'm going to try to line up this x with increasing powers, to this denominator of 6. Looking here, it also looks like this number 3 is 1 more than the exponent 2. But over here, this 3 is 1 less than the exponent there. So it might be useful to take this sum and actually set it equal to, let's see, maybe if I take out a 6 squared from everything, then I'm going to get 1 over 1 plus 2 over 6 to the 1 plus 3 over 6 squared plus, and then so on and so forth. And that's actually perfect because it lines up with this right here. Because I have this 1 at the start, then I have 2 times x. Now let's have x be 1/6, because then when I have 3 times x squared, that's going to be the same thing as 3 times 1/6 squared. Great, and then this 6 squared out front is my a. So if I let a be equal to 36, and x be equal to 1/6, then I basically just have my sum from above. Yeah. So this means y is going to be equal to 36 over 1 minus 1/6 squared, right? Because this a goes here, and then all of these are the x's that are 1/6, and so I plug that in there. And if we do some fraction math, I'll get 36 over, then let's see, 1 minus 1/6 will be 5/6. I want to square that. So I'll get 36 over 25/36. And let's do that same keep, change, flip thing that I did earlier with the fraction arithmetic. So just this way, it's easier for me to see 36 times, so instead of division, multiply. And instead of this fraction, I'm going to flip it. So the 36 is now on top. Hold on. I feel like I made a mistake somewhere. Okay, I found it. When I factored out a 6 squared from this original series, y is equal to this series from earlier, I was factoring it out from the denominator, which basically either needs this to be a -2 instead of a +2 as an exponent, or I need this just to be 1 over 6 squared, or 1 over 36. That way, if you redistribute it, these 6 squareds would go into the denominator of all those fractions. So going all the way down here, this a isn't 36, it's 1 over 36. So let me fix that here, 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 and here. These are all going to be 1 over 36. And then finally, when I do that whole keep, change, flip to rewrite my fraction division, now I can see that these 36s cancel. And so I'm just left with 1 over 25. And by showing that y is equal to 1/25, kind of like I was talking about earlier, therefore, x is equal to 25. So, wow. I didn't have to prove the infinite geometric series formula. Sometimes you can just kind of take this and think of this formula as a given, kind of like how I would probably just freely use the Pythagorean theorem in another video. Maybe even this could just be just a formula that you could find by Googling it. But I wanted to show you where these come from. And so we went through some infinite series. We went through some calculus to take the derivative of these sums. And ultimately, both of those were necessary to prove why x is 25 today. So that's all from me today. Why not show you some Quill at the end? Oh, there he is. Say bye-bye, Quilly. We'll see you tomorrow. Thanks for coming along today. Bye.